writing the expression of magnetic flux. Okay, magnetic flux. Expression. Okay, we know that magnetic flux notation is phi, or sometime it is pronounced as phi. Okay, phi or phi, whatever it is. So I'll say phi. Okay, so this is a notation of magnetic flux. So we talked about before that whenever there is a magnetic field, there is always a magnetic flux, and when we put some plate or any material inside this magnetic field, so the magnetic flux is linked with the material, but we have to express in an equation in order to calculate and so on. So I shall write the expression. First, let me write a plate. So a plate will look like this circular plate. Okay, let's say this is circular plate inside. So this is a circular plate. Okay, so there is a magnetic field passing like this. Magnetic field, can you see? Well, let me use this sketch pen so that it will look much better. Like this. This is magnetic field lines. Okay, magnetic field lines. So before that, we always draw normal, as I have said before. If this is a plate, we used to write normal perpendicular to the plate. Okay, perpendicular to the plate. This is a normal. In this plate have some area, so we write delta S. Okay, delta S is surface area. Okay, surface area delta S, and these arrow marks represent the unit vector. Okay, unit vector along normal to the surface area, normal to the surface area. Okay, and this is the area vector. So there is an arrow mark. This represent it is an area vector. Okay, so this is an area vector. This is a area delta S, surface area, and this is a unit vector. Okay, so we draw like this, normal. So we know that when we put inside this plate inside a magnetic field, so it's like this. This is a magnetic field lines. Magnetic field lines crossing or passing this plate. Okay, so this one magnetic field lines, let me draw like this, and in between this there is an angle theta. Okay, angle theta. Okay, this angle theta. So this is the magnetic field lines. So all together we call it magnetic flux density, or simply magnetic field. So it is a vector quantity. Okay, a magnetic field is a vector quantity, so we represent like this. Okay, and here we have, and this is the component of the magnetic field. This normal is a component of the magnetic field, so we can also represent like this, component of magnetic field. We write like this, B and small n. Okay, small n. This means that this is a component of magnetic field B. Okay, so this is magnetic field. So this is a diagram. A plate is put inside a magnetic field, and some part of it, this part, it doesn't include this, so this area is in effect with these magnetic field lines, which we call the magnetic flux. Altogether, this region is called the magnetic flux. Okay, magnetic flux. It has some effect. Okay, but we know that this is not exactly in parallel to this, so it has some value of theta. So this is what we are going to write the expression. So how do we do this? So now let's take out this part. Okay, it look like this, B, okay, Bn, this vector, and theta. So by definition, we know that magnetic flux. What is the magnetic flux by definition? It is the product of the component of the magnetic field along normal to the surface area. Okay, this is the component of magnetic field along normal to the surface area. It is the product, means it is the product with the surface area. Okay, so this is the expression of magnetic flux, but we want to find out this one. Okay, so it is like this. Now we are going to apply trigonometry. Let's write like this. Okay, so it look like this triangle. Okay, triangular shape. It look like this, which have angle theta, and here is Bn, and here is B. This is the hypotenuse, and this is the opposite side. This is the adjacent side. Okay, but in the lower class we used to study like this. We usually write trigonometrical ratios and this triangular shape like this. So that means this is the hypotenuse. What is the hypotenuse? B. So that in order to easy to look and to understand, I just write like this. It is same. These two are same. So this side, adjacent side is Bn, and this is the opposite side. Okay, this is the opposite side. So here opposite side and here trigonometrical ratios ka kan zir thina nga lower class khan class 9 nge class 10 han in zir to nga chuan hi b hi magnetic field near or magnetic flux density ti boka hi component of magnetic field and Bn normal to the surface component of magnetic field kan ti ka hi ta ani ta boka tian representing then thilpan hi omane chu hela hi chu value control. We don't know this side of what is the value, but we take like this is the triangular shape. Hetian ka da rem ringot ani hi enanom nan achan chu lower class akhan tin triangle kan je ka trigonometrical ratios ka sin, what is sin theta te, what is cos theta te, and tan theta te. We used to study, isn't it? So here we can take, if this is an angle, that means opposite side by hypotenuse is sin theta, but we have the value here, that means adjacent side by hypotenuse means cos theta. Let's write like this: cos theta is what? This is adjacent side by hypotenuse. Okay, Bn by B. Okay, but we have to know that we can express in magnitude. Okay, here let me write magnitude. B is simply equal to like this, the same. So in magnitude, if we want to write, so you discard this vector. Hey, vector notation he in payanga chan ay nang rengani chu cos theta B n by B ti khan kan jek ta ni chu chuan B ka ta lo chawang so this will goes up, so that means B cos theta is equal to Bn. So this is, or Bn equal to B cos theta. So we can put the value of this here. Magnetic flux definition kanetane more according to the definition. So we can write like this. Let me write in this page. In this page. So we know that the magnetic flux is equal to magnetic field component into the surface area. Okay. Now we already know that Bn kha B cos theta continue. So we shall put here in this magnetic flux. Therefore, putting the value of magnetic field component of magnetic field along normal to the surface area, then we can write like this: B cos theta into surface area. Okay, so this is the surface area. Or we can write like this: B, take this here, delta S cos theta. So this is the expression of magnetic flux. So phi equal to B delta S cos theta. More theta is the angle between the magnetic field lines and normal of the surface area. Come in kar kanetani. So it's one he expression of magnetic flux kantichuni. Oh, in vector notation we can write in vector. This is in magnitude. Okay, in vector form. Okay, in vector form we can write like this: phi equal to B dot delta S, where you must put arrow mark. This means that this is a vector quantity and this is also a vector quantity. Okay, so this is magnetic field in vector form. Okay, magnetic field in vector form. But you must know that magnetic flux is a scalar quantity. Scalar quantity. However, this scalar quantity is a product of true vector quantity. This is a vector quantity and this is also a vector quantity. Okay, so it is a product of two vector quantity. It's a product of magnetic flux density into the surface area is the magnetic flux. Okay, so this is the magnetic flux. So this is the expression of magnetic flux. It is very, very simple. So here we can have two cases like this. Let's put number one. Now, what about if this theta angle is 0? If the theta, the angle between this is 0. If theta is equal to 0, then what will happen? You can write, if this is 0, that means flux equal to B delta S cos 0. What is cos 0? It is 1, isn't it? So we get the maximum value. Cos 0 he at lien ber, cos 90 he cos a chuan ate ber 0 nia chuan 1 le 0 in kar ani chu mo chu wang chu cos 0 hi a lien thei ber kha nia chum yom zia chu magnetic flux hi maximum ani maximum we shall get the maximum magnetic flux. Okay, he a lien thei ber chum yom zia chu hi when the plate is in perpendicular, it's like this. When the plate is in perpendicular, normal is perpendicular, and when the magnetic field is parallel to this, normal and in parallel the chuan helai plate hi angilin oma the chuan mark explain tong khan adong dem theiber magnetic field hi adong dem theiber, it will get the maximum amount of magnetic field by this plate. So when it is in perpendicular to the field, or we can say that it is normal, parallel to the normal, okay, normal of this plate. In parallel chi hian theta to 0 ni ha kan ria, and parallel chi hian maximum kan hua. Then what about in case number 2? Case number 2 achon if theta is equal to 90 degree. 90 degree means if the this is a plate and we draw normal perpendicular and the field, hey, magnetic field lines, okay, magnetic field line crossing. So angle between magnetic field lines and this normal is 90 degree. Anita heti la hin a plate hi chu a flat ve thung is lie flat, okay. This one heta hin magnetic field lines kani, so they almost cross but pass away without touching. Untouched manglo tina ni chu tien touch lo chon magnetic field magnetic flux kha effect tu nei vak lo tina ni chu mo effect tu nei vak lo tin kal tlang zel ta tina ni a fu vak lo tina ni plate a khan chu wang chuan in hemi normal a hian normal hemin car 90 degree ni chuan we can also express magnetic flux delta S cos 90 chuan, so cos 90 equal to 0 tro chu wang chuan, so the minimum magnetic flux 0 kan hudoni. So B delta S cos 90 is 0 into 0 ni doni chu wang chuan, this will be the minimum magnetic flux, minimum ani doni om zia chu touch tu nom manglo magnetic flux effect tu ka nei tlemper tinani chun come in car pahnia ka chun it may be 30 degree, it may be 50 degree, 40 70 ka chu one I chun claim veka hey I chun it will be less than this, however it will be greater than this in between, okay. Hemi in car kha di chun flux khan om thei vek thowa 30 degree, 40 degree, 50 degree, 60 70 ani nga 80 90 hemi in car jong song ka chun om thei veka hey the greatest, it will have the greatest effect magnetic flux, and here we will get the minimum amount of magnetic flux kan hudon tani chu min car ka chu om thei vek chu wang chuan the khan plate kha avir khan when it is rotating we will get the maximum magnetic flux as well as sometimes the minimum magnetic flux, okay. So it will increase slowly and then decrease slowly again. It's keep going on like that. The khan kal tani chu magnetic flux om zia chu ni tani it's a magnetic field a khan thil kan zuda khan plate an ye moing po wire po ni se coil po ni se kan zuda khan magnetic flux khati chet reng khan kan rotate in mo current alternating current kan pek in mo adang lam reng khan magnetic flux kha effect kha adang lam ve renga in atam ber lai atlem ber lai che ve reng tani chu mo tu ting chon ape chok thin ni aina current po kha chu ting chon adang lam tani chu mo. So that is all about expression of magnetic flux.